Here's the question of the day. How much does an Oreo actually weigh? All right. So we wanted to estimate the average weight of an Oreo to determine if the average weight is less than they advertised. He selected a random sample of 30 cookies and found the weight of each Oreo in grams. The mean weight is, you see it in there, X bar is 11.1921 grams. Standard deviation is 0.0817 grams. And then it says, let's make a 95% confidence interval to estimate the true mean weight of an Oreo. Because why not? Now, point estimate. What's our point estimate? Do you remember what a point estimate is? The what? The medium.
Median, like, in between
The middle. It's the middle, yeah. Oopsies. That's not what I meant to do. It is the middle of our interval, right? So we start with our sample statistic. That's what starts it. So what is our point estimate in this case? It's the X bar, right? 11.1921. All right. Then we're going to look at identifying, again, population, parameter, sample statistic. What is the population we're interested in here? All Oreos. Good. And the parameter, what is it about Oreos we're looking at? The true weight, true mean weight. Specifically, remember when it's parameter, we use mu. The sample, he took a sample of size 30 Oreos. And the statistic is the result of that sample. He found it to be 11.1921 grams. Okie doke. Then it says, was this sample a random sample? Yes. And why? Do you remember why it's important that it's random? So you can apply it to the whole population. Good. Yes. Why is it important? So we can apply results or generalize the results to the whole population of Oreos, or whatever it is. Now, before, when we did sampling distributions of X bars, we said it was sigma over the square root of n. Remember that? But sigma indicates that we know the standard deviation of the whole Mama Jama population, but to do that, we'd have to know the mean. We don't know the mean, so we don't know our standard deviation. But what do we know? We know this little guy, the S right here thing, right? We do know S of X. That's the standard deviation of the sample. Okay, we have that. And if we just replace sigma with that, this is what becomes, again, remember standard error gets changed, the name gets changed just a little bit. It's called the standard error. So if we plug in that standard deviation, 0.0817, and divide it by our sample size of 30, I get 0.0149. All right, and then would it be appropriate to use a normal distribution? Oh wait, we didn't do the second part, did we? Hold up. So up here we checked the random condition. Now it says on 4, it says verify the condition is met. What condition do we have to meet for standard error? Do you remember?
Is that like the 10%?
Yeah, good. It's that 10% condition. That 10% condition. So let's think about this. Is 30 less than 10% of all Oreos? I'm thinking so. I think that's a fair assumption, wouldn't you? Okay, easiest thing to figure out, right? But, so there's our 10% condition, and then here's the normal condition we've been doing. And these will become very repetitive as the course continues. Would it be appropriate to use normal to model the sampling distribution of X bars? Justify your answer. All right. Do you remember how to decide if it's normal, if it's a mean? What was that called? Do you remember?
Central limit theorem or something?
Central limit theorem. Large counts is the NP greater than 10 thing. That one only applies to proportions. Means is central limit theorem. Okay, so it's been a minute since we've done this, so that's fine. So since our n is 30, which is greater than or equal to 30, we can say by the CLT it's approximately normal. And that's all you have to say for justification. If that's the trick you're using, that's it. Becomes your favorite by the end of this, I promise. All right? Now, when finding the margin of error for a confidence interval for proportions, we used Z star, right? But we're no longer using proportions, and it means we have to use a T star. So we're actually changing distributions. We're not going to use the standard normal distribution, which we've been friendly with all year long. Okay, there's my standard normal. T distribution looks different, and it looks different based on sample size. Let me show you. A T distribution is a little fatter in the tails and shorter in the peak. That is one way to do the T distribution, and somebody really smart did all the calculus to figure out the area under that curve for a certain sample size. If my sample gets bigger, this starts to get bigger. And eventually it will look just like the normal if my sample is large enough. But with means, we have this special case still, all right? So we have to use what it's called the student T distribution. But we just abbreviate by calling it the T distribution, all right? There's some little interesting history behind it, and I'll show you a little video at the end. It actually came from Guinness Beer. The Guinness Beer Factory, a guy that worked there developed this. So it's a little history and stats, right? With this, since the curve does change based on your sample size, we have to consider something called degrees of freedom. Okay? You have to have degrees of freedom with the T distribution, and it's really just n minus 1. That's all it is. Sample size minus 1. Now, what T star is needed for a confidence interval? We're not going to use table B. We're going to use your calculator like we've done before. But in your calculator, you're not going to use inverse norm. You're going to use inverse T. And when you do, it's going to ask you two things. What's the area and what's the degrees of freedom? So you may or may not remember, we're doing a 95% confidence interval. If that's true, then what's the area in the tails? 0.025, right? So in this case, we're going to put 0.025. Degrees of freedom is sample minus 1, so it's 29. If you want to do it in your calculator with you, I'll give you a second. That'll give you the T star. That gives me a T star of plus or minus 2.045. All right, now it says calculate the margin of error, because remember that's going to be T star times the standard error. That's the margin of error. So we just found that 2.045 times the standard error that we found on the previous page was 0.0149. When I multiply them really quick, I get 0.305. Then it says calculate the 95% interval using the point estimate. That was that original X bar, 11.1921, plus or minus this margin of error we just found. 0.0305. Okay? And when I subtract, I get 11. 11.1616 and 11.2226. And this is grams. All right, interpret. Same sentence structure as before. How did this interpreting the interval start? Good. We are 95% confident that the interval from 11.1616 grams to 11.2226 grams captures the true mean weight of, of an Oreo. All right. According to Nabisco, they advertise that an Oreo weighs 11.3 grams. Does our interval provide convincing evidence that the true average weight is 11.3?
No.
No. Why not?
Does it fall between like the interval that we found?
Yeah, that 11.3 is not even in our interval, is it? It's higher than the interval, right? So we would say, does it give us evidence? No. We'd say all the plausible values in the interval are less than 11.3 grams. So we cannot say that they're telling us the truth. We don't think they are. So far, so good? Not too different than proportions, is it? You just have to remember that T-star thing, okay? Now, let's do the next page. Now, with this, I use this little memory thing, a zap tax. I think I mentioned it in the video, maybe I didn't. Zap tax, and this just helps me remember that Z star goes with P hat, T star goes with X bar. If you need it, it's there to help you, okay? You don't have to use it, but it's just there. Now, let's just summarize this. Okay, so T is used for estimating means. Degrees of freedom is something we have to use with T distribution, and that's just n minus 1. And these instructions are if you're using the table. We're not using the table. We're going to use inverse T in your calculator. It's going to ask you for area, and it's going to ask you for degrees of freedom. That's how you're going to find your T star. And then the conditions, same conditions we've talked about over and over now. Random has to come from a random sample. Our 10% condition, which is really just testing independence. And then lastly is our normal condition. The normal condition. So in our last example, n was greater than 30, so we use central limit there, right? But we also have other ways to find out if it's normal. If the population is told to us this normal, we know the sampling distribution is normal. And if that doesn't work, then if we have to make a dot plot of that sample data and look for strong skewness or outliers, that'll tell us if we're normal enough to proceed. Okay? So this is going to become more familiar as we do more examples here. Okay, so let's look at this application. Let's see what you can do. All it's asking you to do on A and B here is find the T star for a 98% confidence interval with a sample of 26 B is a 99 with a sample of 85. And then C is checking the conditions for this question. So I'm going to give you a few minutes to do that, and then we'll check your work, okay? See how we do with it. You get it? You get it? Okay. So you got a T star on that part A is 2.485. Part B is 2.636.
So there's no extra step after that, it's just that?
Would you need to
Well, these questions are just asking you for the T star.
Okay.
It's not asking for the interval.
Okay, that's what I.
You probably should put plus or minus on it, yeah.
Okay.
Yeah, to be more accurate, plus or minus, yep. And then checking conditions on this population, all right? It clearly states it's a random sample, so that's not hard to find. 1640 is less than 10% of all adults. That's easy to reason out. But then normal, this was throwing people off because look at the histogram. It's pretty skewed, isn't it?
Yeah.
But remember, the population can be really skewed, but the sampling distribution can be normal. That's way before Christmas. And that's only if the samples are greater than 30, and we do it many, many times. That's where central limit saves our butt a little bit, right? All right? Easy enough? We handle this? Tuesday when we come back, we're gonna do another practice interval with means, and then that's the end of the chapter. It's not so bad. Now, before I completely lose